Today we are happy to listen Vanden Eijnden from Korean Institute on CFM, which will talk about beyond diffusions with stochastic interference.
Thank you. Thank you very much for coming. It's a pleasure to be here. I think it's the first time I'm visiting the lab, actually. So I'm at Courant usually, but I'm spending some time at the CFM, which is an hedge fund in Paris, for another years. So what I would like to do today is discuss a little bit advances in Gen AI that are based on transport of measure, and I'll try to explain that during the talk. And it's a joint work with many people at this point, but let me just point out Michael Albego and Nick Boffey, because they're the one with which this project started, and the result that I'm going to explain to you were first obtained. Okay, the rest is okay. So I don't think I need to tell you that there's been like a revolution into what one can do with this Gen AI. Okay, these are a few examples. You can put sophisticated prompts like that and generate fake images, like with all the ethical problems that come with it. But you can also do things that are more interesting from a scientific viewpoint. Like, for example, you can, predict the weather, where the prompt is the state of the weather today or a few days ago, and then what you're predicting is the possible future, so with probabilities of what will be the weather tomorrow. Or you can fold proteins, so predict folded structures protein, where the prompt is the primary structure, so the chain of amino acid, and what you get is the folded structure. This work actually earned the Nobel Prize to Baker and Asanalis for, this is AlphaFold. Okay, so I'd like to explain a little bit, what's the machinery beyond this. I know that most of you might be familiar to it, but I'll try to put a different twist on it, explaining what we have done. But I'll start, with the basics. So these are applications of what's called unsupervised learning, okay, where the basic premises is that you assume that you have, some data that's available to you that is unlabeled and unorganized. If you have label, it's better, but if you don't need to have them. And then you make a working assumption, which is to say these are samples from an unknown probability distribution. And what you're trying to do is to learn what this distribution is in a constructive way, meaning in such a way that you can generate more samples from this distribution. Okay. So the picture in 2D is elementary, right? You have these black dots and they are drawn from distribution you don't know, and you're trying to find out what it is. But what you need to keep in mind is that what we would like to do is to do this in very high dimension. And so where the data points are, for example, the image is a little bit too small, but every one of these faces here, picture is a data point. And so if you pixelize that, say 512 by 512 or 256 by 256, you're in, this is the dimension of space times the number of channels that you need to, for every pixel to represent it. Okay, and so what you're making the assumption is that the black dots are these images that live in this, gigantic, highly dimensional space, and you'd like to do the same thing. So this problem is a well-known problem, of course. It's just density estimation, and it's an old problem that is intractable or thought to be intractable by by standard methods. You can't bin space when it's high-dimensional, kernel density. All of these things don't work. Okay, and so there's been recent progress using tools from machine learning and AI in particular, and that's this whole business of Gen AI. And the progress, the main progress has been, quite interestingly, by using transportation of measure. So what is that about? Well, it goes like this, is that the aim is to construct a stochastic differential equation or an ordinary differential equation if you drop the noise, which has the property that if you start this process with an initial condition that is sample from a simple base distribution, think Gaussian or uniform, okay? you adjust the drift in such a way that at time t=1, say, the solution becomes a sample of a certain target distribution. Right? Okay. So this is dynamical transport of measure. There's many people who have worked on this, right? And if you manage to do that, you have a way, a practical way to generate sample from U1 that's actually fairly simple because you just need to generate the sample from the base. If it's a Gaussian, that's easy to do. Then you need to integrate this OD or SDE, which you can do numerically. That is a very well-known technique to do that. And you get a sample from your target. Okay, and this little picture illustrates what that is. So the noise for this data set is called the flow data set. The noise that you see is just the noisy image that you see at the beginning, and this is a flow that has been trained in such a way that it produces images of flowers. If you want to do that with protein, well, the atom of the protein are just thrown at random position is your base. That's the beginning of this movie. And then you train them so that they move in such a way that what you get is a sample of the folded protein. Okay. And so far, so good. But of course, the difficulty here is that you need to construct this velocity field. So there's many results that exist, in particular, that gives you existence of velocity field that transport one measure on another. But we are interested in trying to do that in a practical way, and that is by trying to find a variational formulation for the B, for this drift, that is then amenable to computation. And I'll explain what that is. This is the toolbox of machine learning is about doing this. Okay, so the feasibility of this program was demonstrated not so long ago. That was really the breakthrough in this area in a series of papers. And this is actually pretty recent, but the paper that really was a breakthrough are these two, and this one, the paper by Song and Herman, where they constructed such a drift by using the following procedure. They say, well, turning data into noise, say images into noise, is easy. You can just noise them, for example, by passing them through a stochastic differential equation whose invariant measure is just Gaussian. Think Gaussian-Uhlenbeck, for example. So you pass data from a measure that you don't know, or distribution you don't know, through an Gaussian-Uhlenbeck, it will turn into noise. And then, so the noising easy, and then what you'd like to do is to time reverse this diffusion in such a way that what you get is now a diffusion that can take samples from the Gaussian and turn them back into images. Okay? And you can use known results from stochastic process theory, going back to Nelson, Fulmer, Anderson, that tell you that if you time reverse this SDE, well, you can write it down explicitly, but what you need to have access to is what's called the score function, which is the grad of the log of the time-dependent probability density of the process. Okay? And the breakthrough was to realize that this object can be learned by regression. Okay, and there were other, they were work by Eijnden and Vincent that actually gave an objective function for this score, and so that was amenable to calculation in such a way that you could learn this by regression, which gave a practical way to actually access, this SDE by postulating that one, learning that, and running it in time reverse. Okay. And now what I'm going to explain to you is that this picture can actually be simplified somewhat and then recovered as a special case, and that's what we have done with Michael and Nick. And so I'll spend a few slides to just explain that, because in some sense it's elementary. So and I think it simplifies things quite a bit. So what I'm going to be discussing is this stochastic interval that also go by the name of flow matching or rectified flow, because there were papers concurrent, to us that did that. The flow matching is the Littman paper, and that's, I think, is the terminology that is sticking these days, but I keep calling them stochastic interval. Okay, so the idea is simple. We're going to construct a stochastic process that interpolates between the two measures. but we're going to do that not in the measure space, we're going to do it in sample space. And the way you can do that is by taking sample from your base, sample from the target, and then, for example, multiplying them by time-dependent coefficient that have a certain that say smooth, differentiable, and that have the right boundary condition that guarantee that if you evaluate this process at t equals 0, you get x0, and if you evaluate at t equals 1, you get x1. You can, for example, think about simply the linear interpolation that is there, right? And you need that these two guys marginalize on mu0 and mu1, but they could potentially be coupled. If they don't, you just draw them independently. Okay, so here's a little picture to explain that. Imagine that this is mu0 and this is mu1. You have access to samples on both sides. Okay, you're constructing this process by pairing, say, randomly one guy at that end and one guy at that end, and just making a straight line. This is the point over there. Okay, and then I mean this induces motion. So I'm just showing you the movie on how the sample would move. So these are, if you wish, realization of IT as they move from one to the other, right? And then this in turns induce a motion of the measure itself, of the law of this IT, and you'd like to learn what this motion is.
So here the vector field is deterministic.
The vector field is deterministic. I'll insist on that later. There is no diffusion here, right? In fact, I'm going to do something which, I don't know if it's allowed here, that I'm going to cheat. I'm going to tell you that you can completely forget about the law of stochastic calculus and just do everything with, elementary calc 1, like, math from the lycée.
So it's like displacement property.
Exactly. Yes.
You mentioned the pairing. The pairing, you do it at random just for once. I mean, you have x0 sample, x1 samples, and you choose the pairing at the beginning, and you.
In the learning, that's not the way we do it, because at the noise end here, typically you can regenerate. But yes, in principle, the pairing that is gone, you could make it to be independent. Indeed, you don't have to. You could imagine that if you have, for example, the optimal transport coupling, you could use that one. If you have that, typically your problem would be solved to begin with. So it's not the practical case, but you could. Okay. Okay, and then there's the main result that, in fact, is quite elementary, is that the law of this process is the same as the law of an ODE with initial conditions that are drawn from the motion, the base, provided that you use a drift which is given by the conditional expectation of the time derivative of the interpolant at a given position. Okay, so the picture is actually quite simple. That among all of these rays that I'm not showing you anymore, the one that passed by this point can have different velocity at, for the interpolant, which is the I dot. And then if you take the expectation of this, you get that guy. And this drift has the property that the law of these two processes at any given time is the same. As processes, of course, they are very different, but as their law at every time is the same. Okay, so that's one result. I mean, I don't know. I mean, is this a bit? This is. I'm not going to go through that. This is chain rule. The proof of this statement is extremely elementary. You take this function. The definition of the the measure of the interpolant is this. You take a derivative. You use the definition of the conditional expectation, and you get a transport whose characteristic is just that. And it's as simple as that. Okay, and the way, so this generates a transport, right? Which is that if you have learned the B, right, generating IT is not a generative model because you need samples at both ends. But if you have learned the B, you only need samples at this end, and you pass this through that, and you get sample at the other end. This, for example, is the flow that you get if you go from in 1D from a Gaussian to a Gaussian mixture with 3 modes. And this is not a cartoon; this is the actual flow. Okay, and this is not OT, but you can bound the cost in W2 of the transport with the property of the interpolant. Right. So we're not necessarily. I'm going to go back to that later, but we're not necessarily interested in doing optimal transport in the sense of Morgan, Ampere, Kantorovich. We just want to have a transport that generates one transport. right? And now, why is that practical? And this is the part that I will, skip under the rug, but is like what makes all of this really like usable. Is that you can take the L2 characterization of this conditional expectation to write down an objective, which is to say that this B is just, the argmin of the objective that is written there. So it's not the condition, it's just the expectation over all B in the appropriate class of B evaluated on IT minus I dot squared. Okay? And this loss, or objective function loss is the balance of machine learning, is tractable in the sense that you can estimate it very easily on samples. So that means that in a way you're in business, because what you can do is that you can estimate the loss given any B test function B at on your samples. Then you can parameterize the B to do the optimization in some sufficiently expressive rich class. These are deep neural network, transformers, UNets, whatever. And then this loss then becomes an objective for the parameters that you have in this neural network. And then you're just doing the optimization using the standard tool of machine learning, which is by stochastic gradient, etc. Okay, so just optimize that, and then you get an approximation of B, of the minimizer, in the class that you have chosen. And I'm not going to explain much more about that. That's like all the toolbox of machine learning, but I will use these results. All the numerical calculations I will show you later are done by doing essentially this, right? And this is what is done in any, machine learning code, So that first result. There's another result that you have, which is, and that's like, I'm going to slowly go back to diffusion, which is that, okay, so I told you that the distribution, the time-dependent distribution of the interpolants satisfy a transport equation with the drift. But then you can use a little identity to actually rewrite this transport equation into a diffusion equation, a Fokker-Planck equation, or what Kolmogorov equation with a non-zero diffusivity, by using sort of a very simple identity, which is that if you know the score, the score, this S here is it's in the way, forgotten to write that down. Okay, the S is the grad of the log of this mu t. Sorry, so the st of x is the gradient of the log of mu t, or I mean, this is a bit stopping. This is the density associated with that. If you know that, then this term, the divergence of this, is the same as the Laplacian of mu. Okay, and so this means that if you estimate this score, you can actually turn your transport equation without noise into one in which there is noise. And you can do that by realizing that this is application of Stein formula, that in fact, this score can be re-expressed in terms of this drift itself. It's a little identity. So if you learn the B, you have access to the S, and if you have access to the S, you can write down the diffusion equation. Okay? And why is that useful? Well, it's useful because once you have written this, that means that you can, sample this distribution using no longer the ODE, but an SDE with a diffusion coefficient that can be adjusted post-training. You can decide what you want to do later, right, by using this. And the results just say that the law of this at any time is the same for any value of epsilon. As a process, again, is different, but the law at any time is the same for any epsilon, and is the same as the one of Vanden.
But in practice, why would you like to transform it into SDE in the ODEs for easier to integrate, right?
I'll get to that in the second half of the talk. I'll explain. Okay, so but just to so that we understand. So the framework allows you to do this. That you're taking a base and a target distribution. You're constructing an interpolation by choosing this coefficient alpha, beta, and there's a latent variable that you can add. that gives you a connection in distribution space. Like, for example, if you go this way, that way, they all have the same endpoint. And then once you have done that, you can learn a drift, and then you can, from this drift, deduce a score, and then you can generate samples by either simulating the ODE or the SDE at different noise. And these are just realizations that you get in this process. And each time, if you have learned the drift appropriately, what it will give you are samples at the end of your target. Okay, this is maybe a picture that illustrates that in a way which is more visual. Suppose this is a unique sample here of a noise. And then if you have learned a drift, so this was learned on this data set, which is flower, and then you solve the ODE, from this noise you get that flower. And then you can redo, you can use it by, and if you were to redo it, this is just this defines a deterministic map. But you can redo this simulation at different level of noise just by tuning this epsilon t, in which case this same initial condition will not generate different flowers, and the diversity that you get at that end will depend on the level of the epsilon, the diffusion coefficient that you put in. Okay, and to get the full distribution in either case, you would need to sample at that end different initial conditions.
On the left column, you always have the same initial noise level. I mean,
For this illustration, yes. If you want to sample the right target, you will need to sample at that end everything, unless you take epsilon going to infinity. Okay, and then one of the mystery here that I will maybe address a little bit, I mean, discuss a bit later, but probably not, is that there's something which is remarkable, that when you do this, you actually get a model that in fact works in the sense that it generates flowers that are not seen in the data set. For example, if you take that flower, this is the one that has been generated here, and you look in the training data set, what were the flowers that are the closest. This requires defining which distance you would have at this L2 in pixel space. These are the flowers that were the closest. And you see that they all have features of that, but none of them is exactly this one. So it has really generated a new flower in some sense, and that is quite remarkable and not very well understood. Okay, and you can, I'm a little bit these days, I'm a little bit embarrassed to show that, but you can scale these things in a way which is like, of course, OpenAI can scale them, but we can also do that in-house. So these are calculations that were done with a colleague at Grand Séminaire. Is a big shot in computer vision, but it's like if you use neural networks that are sufficiently expressive, you can get generative models that create images of this. These are all fake images, okay? That are just like, this is on ImageNet 512 by 512, but what you actually do is that they are classes. And so this is a prompt where you ask it to create, I don't know if it's a tiger or it's a big cat, I don't remember, but this is what you get, and similarly for these images, okay? Now, and this technology is not the one that, in most image generators are being used. Now, you can use this framework to do tasks that are a little bit, more interesting than just generating images. Illustrate them again with images because it's pretty, but you can, for example, do denoising. This is an example of denoising. So here, you can exploit the formalism by, in all what I have discussed, it's not necessary that the base be a Gaussian. That's something that people doing diffusion are tired of too, but here you can take anything you want. So you could imagine that if you have images that are noise, you have pairs of images, one from the target, these are your clean image, and then you have noisy images. You can have these pairs, you can declare this is sample from the target, these are sample from the base. And what you can try to do is just to do a transportation that will take these images back to their target. Okay, and that's an example of what you obtain in that case. Right? So this is on what's called the test set. So it's afterwards, when you have learned, you give it an image that it has never seen, you tell him what is the bird that you would get if you denoise it, and that's a denoised bird. And it's a generative process. If you do it many times, you would get many different birds here, but consistent with that one, and similarly for the image data. Here's another application of the same type. If you give it, you train it on pairs of image where one of the image at the base side is simply the target in which you have taken masks at random position that you have noised. You can train model to denoise image or to in-paint in this case. And these are the type of result that you get, where again, there is a thing that is quite remarkable, that these are images that have never been seen in training, but you see that the in-painting that is being done is very good. Right? You get the sale there and not the whisk.
The noise replaces the image or it's added or multiplied to the image?
So you put a mask, and then what you have here, the samples are just samples where the pixels that are not masked are the original one, and the pixels that are masked, you replace them by noise. Or by zeros, if you want. This is not very important. And then what the process does is, if you sample the noise here, you get, again, it's a generative model. So you're really sampling the posterior in principle. And so it will give you variation here that are consistent in principle with what it does now. Okay? Okay, I don't want to bore you with too many of these examples, but maybe this one is kind of just, if you've never seen this, it's actually quite impressive. Like so this is something where you do conditional generation, where you take movies and you take a few frames of the movie and you just train the model to predict the next one. And then you take the next one, you put it in the conditioning, and you go like that. So you do generation in sequence. Yes.
There are never cases where, from a given noise, you just get nothing at the end?
Probably if you push it, you would indeed get weird stuff. Yes. Yes. But most of the time, right. So this, you're going to get that later. This has to do with what exactly is the probability distribution of images. There's this working assumption that these samples come from a probability distribution, which is a reasonable assumption, but it's a very way what at the same time, and we have no idea what this distribution is to begin with. So, okay. So here, what you see, and this is kind of illustrating what the capability of these models again is that these are, so here is the original movie on the what you have, and then this is what the model produced. This again, of course, in the training, he has never seen this little movie, and then it produces movies where only a few frames are common, and then it generates a potential future, like weather, if you wish. And you can see that without inputting any, this is just, working in, there's a bit of a representation, it's not very important. Without inputting any physics, essentially, you get movies that are all a little bit different, but all sort of reasonable. Okay. Okay, so I'll go back a little bit now to theory. So first I want to explain why this, and we connect this with diffusion. We did diffusion at the beginning, so let me connect that. Yes. I'm not sure I understand. So the images that I showed are done in pixel space. Typically, when you look at the big model that they're, Nano Banana, these things, they don't work like that. They work in some latent space so that they can get to bigger resolution. And the movies were done in a latent space that I showed you. Okay, so there's something there that guaranteed. The latent space allows you to compress the representation so that you can do the diffusion in a slightly smaller space. It's still a very big dimensional space. Okay, so let me go back to this diffusion. We've seen that, and just explain to you a little bit why, how you can connect that to interval. So if you take an ocean-based process, and in a time that I denote tau because I will change it, and you start with an initial condition that come from the data distribution, you can use Journal principle to store this SDE, and then in low, the solution of this SDE can be expressed this way, where this is not true in the sense of process, but at any given time, the noise term can be represented this way, where x0 is the, So what you see is that it does exactly what it's supposed to do, which is that it takes the data and feed it exponentially fast and replace it exponentially fast with noise. Okay? And now that's the original process, but once you have realized that you are doing this, well, you see that if you tie yourself to simulate this in reverse diffusion, then you're tied up to the point that was there. But you can do something which is different. You can realize that if you change the time, you can actually put everything here on 0, 1, like I was doing. And this is just a specific choice of an interpolator. And so this means that at this level, first of all, you have eliminated this bias that comes from the fact that in principle, you only reach the Gaussian here at time capital T going to infinity. So you can remove that because this mapping maps 0 infinity to 0, 1 or 1, 0. And you can sample now, this process in the direction that you want from noise to data in different ways than using the time reverse diffusion. In fact, you can choose. That's what I was explaining. Okay. And so it looks like maybe we have not gained an enormous amount in practice, but conceptually, we have done something which is interesting here, I think, which is that we have realized that diffusion, in fact, sort of entangled two operations that should be thought of separately. One is to make a bridge between target and base distribution, which you can do at the process of the samples, as I explained. And then is how to sample the corresponding time-dependent distribution that emerge. And these two things really are separate. In the diffusion, it looks like they are not, but they are really separated things conceptually. And if you open this, then you can do more things. I don't know if I should discuss this, then maybe skip it. You can link this to denoising, which is the standard. If someone is interested, I can discuss that later, but in the interest of time, let me just skip this. And now I want to explain a little bit. Okay, so what I want to do next is to explain a little bit what you can do with the formalism if you leverage the flexibility that it has, right? And in particular, what I would like to explain a little bit is that there are two knobs here that give us freedom, which is the way you define the interpolant, what is this alpha and beta, that we know alpha t, beta t, and then there is the noise coefficient. So let me explain what you can do on both aspects. Okay, so the first one is like this. So there's two observations that you can make, which is, so this is about the alpha and the beta t that you have in this process. Well, I told you can take alpha t and beta t to be, say, 1 minus t and t. And diffusion gives you another one, which is, t and square root of 1 minus t squared. But you realize that you don't need to take scalar function of time. You could actually take operators or matrices, right? As long as they satisfy the right boundary condition, they will do the job. Why do you want to do that? Well, it's because then you have a freedom by which you will turn your noise into data or data into noise, for example, that becomes scale dependent if you use operators. Okay, that's not conceptually, that's not a big deal. It's just saying, well, don't do that as scalar, do that as operator. But then there's something else that is more interesting that you can realize is that, in fact, there's no reason why you should prescribe them beforehand. There's this time in diffusion. You don't need to put time. You could actually think about this simply in terms of the operator. Let me try to explain. Okay, so these are different choices of alpha and beta that allows you to interpolate between noise and data in different ways. Okay, so this is, for example, what you would get if the alpha and beta are diagonal matrices that allows you to move the pixels individually from noise to data. Then, if you choose them differently, you would be able to denoise this way or that way or that way, or in fact, any other way if you have all the operators. The same thing here with, different type of operator, okay? And so, the observation that you don't need to do that. You don't need to choose this path beforehand. So let me explain this maybe in the following. So suppose that you think about the interpolant not as a function of time, and it's 0 and it's 1, but as a function of two operators, linear operators. Okay. Then, okay, you realize that. So I'm going to, build up on this. You realize that you can, you can define conditional expectation of this similarly as we were doing before, where now you do the conditioning by picking, fixing alpha and beta L upon x, and you calculate the expectation of x0 and x1. This is essentially what we did before. But you do it not as a function of time, as a function of alpha and beta. Okay? Then you realize, in fact, this is practical because these are conditional expectations. So if you put some probability measure on these operators, you can actually learn them globally on whichever set the distribution of these alpha and beta is supported. Like, for example, to be concrete, if you take these guys to be diagonal matrices with a little bit of an abuse of notation, you can represent that as an Adamant product between two vectors, which is the diagonal vector of alpha. And then the natural thing that you would do is to equip, you take beta equal 1 minus alpha to reduce a little bit more. And then the natural thing that you can do is that for alpha, which is now a vector, right, you can take it to be uniformly distributed into the hypercube. So that means that you have access now with this process into something where you can choose which pixels are noised or not a posteriori. Okay, and then you can show that if you have learned this sort of multitask drifts, you can a posteriori decide how you're going to move in that space to actually do generation that is multitask. So you kind of, what you do is that instead of relearning a model each time, you do a much bigger learning at the beginning that gives you access to all the models that you want a posteriori. Okay? And explain maybe how you can do that. These two examples, let me show this one first. And again, I'm a bit embarrassed. This one probably I really should remove, but okay. You'll allow with his friends from the United States, so this will be allowed. So here's the kind of thing that you can do. You take an image like that one, you take this cat, you don't like his eyes, you mask them, you denoise. You say, well, actually, I don't like the denoise. And this is all done with a single model, where it's just, with respect to what I was saying before, you just take, you choose what are the alpha and the beta that you do a posteriori. You have learned a universal model that can actually edit cats or any image that were in the class that you have trained the model on, right? And similarly for the faces. Here's another example. You can imagine that the data that you have is just a walker that is going in a maze randomly without ever stopping. It's a maze without exit. And then you can imagine that there are time slices here. This is what you vectorize for your path. That's the way you describe the path. And then you can learn something in which the alpha and beta are again Adamant product. What does that allow you to do? It allows you to write a model that a posteriori can be used to generate paths that go in the maze from any point to any other point, a posteriori.
This is going down there. It's the same maze. Yeah, it is the same maze.
Yes, that we could try to kind of enlarge this a little bit and do multimodality over all the mazes. But here is like the data set that was done is just a very long trajectory of the walkers that moves in the maze. Okay. Okay. I'm going to skip this in the interest of time, just because there's a lot of math. Actually, it's not complicated math. It's just a lot of formula. But you can do this to actually do posterior sampling. You can tilt distribution. If anyone is interested, I'll discuss that later. But I want to go. Okay, so that was about the fact that there is flexibility in the alpha and beta. Now I want to explain to you something else, which is, there was a question: why use the SDE rather than the ODE? Okay, and well, there is a reason actually for that, which is okay. So let's understand something. I wrote this equation before, and I told you that this term and this term cancel each other exactly. Of course, this is only true if the S that you put here is the grad of the log of the nu. In general, you're learning these things, so you have estimated B and then you have estimated S from B. They are no longer they are not exact. And so that means that the distribution that you get if you use this equation depends on the value of epsilon. Okay? And so you can ask yourself, well, which epsilon should I pick? It's a natural question, right? And so there's a way to phrase this problem. So first of all, there's a way to phrase this problem, and I'm going to do it in one specific case because the calculation is sort of elegant, which is in the case where the base distribution is a point mass. So you take a point mass as not a Gaussian, just a point mass, and then you can write down an SDE that from this point mass is generating whichever distribution you have at the other side. And then you can write down a family of these SDEs with a diffusion coefficient that you can adjust. And these are the formula that you can write down in that case. And then you can ask yourself, okay, so which epsilon should I use here? This is the exact one, but you don't have access to it. Okay? So one way to phrase this problem is to say, well, okay, I have my exact process that I don't know. I have the estimated process, the one that I have access to. And so what I would really like to do is I would like to minimize some form of distance between the solution of this equation and the solution of that equation. Yes.
You want to take the log of the probability distribution, you need it to be non-zero, right? And if you take just the point mass, it's...
Yeah, there's a little singularity at the beginning. It's okay. I mean, as soon as you have any type of silence because of the noise, you're fine. Okay? And we can discuss that later. Okay, so one way to do that, which the one that we're going to take here, you could take other criterion, is that you can take the relative entropy between the solution of these two equations in path space. It's not exactly what you would like to do because you don't really care about what they do in path space. You really only care about what they do at time t. For one, that's harder because you don't have access to the solution. Whereas if you do, you look in path space, you can actually write down the K divergence of the relative entropy between the two path measures because this is just Jessenov theorem. Okay? And what is interesting is that this guy becomes an objective function for the diffusion coefficient that you put in the equation. And interestingly, you can show that you can minimize it explicitly. So it doesn't depend, I mean, the minimization doesn't depend on the B and the S that you don't know. There's universal diffusion coefficient that depends only in the interpolant that minimizes the KL divergence between these two processes. And it's given by that. Okay. And more interestingly, maybe, and this is something that maybe people in the audience know, I don't know, is that you can, once you have obtained the solution, you can sort of analyze it a posteriori, and what you realize is that it's actually a formal process. So that the optimum that you get is a formal process. So what is a formal process? It's a Schrödinger bridge process between a point mass and a non-trivial target, right? And that's the case where it can be solved sort of explicitly. And this shows that optimizing the impact of the estimation error on the generation error gives you a formal process, which, as far as I know, is the new characterization of these processes. Okay. I'm running surely but quickly out of time, so let me give you a few extensions of this. First, there's one thing that you can try to do. So these are kind of active, research thing, which is that instead of, there's a problem with this relative model is that they need to integrate. The generation amounts to integrating an OD on SD. So it is simple, but it is costly because you need to evaluate this drift as often as you need to take steps in the ODE. Okay? So what you may want to do is to learn the flow map. And the flow map is just this little picture. It allows you to do steps of arbitrary. It's the one that propagates the solution of the ODE over finite times, pairs of times. And it turns out that you can again, this is always the same little mental exercise with machine learning, is that you can say, well, okay, is there a loss that I can write down for this guy? And if you work a little bit, you realize that there is a loss that you can write down. And so you can optimize this loss either by distilling a velocity field, the drift that you have pre-learned, or in fact, by doing it from scratch. It's a more complicated optimization problem, but what it gives you is a map that then allows you to do generation in one or a few steps. And again, remarkably, it works. So these are, again, very in-house small thing, but it shows you how you can generate images by taking, instead of 16 steps, it's not that much for DOD, but just 1 or 2 steps. Okay. Recently, we have generalized that, and this is, I think, too much to explain in great detail, but we have generated that to do diffusion on the probability simplex. Why do you want to do diffusion on the probability simplex? Because when you want to do word generation or text generation, you know that LLM tokenize. These tokens you can embed it into a simplex, so in probability space, where every token is a one hot vector on the simplex. Okay, and the way large language models are working right now is that they learn a categorical distribution that tells you which is the next token given the context. And so they need to do autoregressive generation. Okay, and this is extremely costly because the tool that you use, probably use Claude Code or whatever, or, you know, Gemini, right? Manipulate trillions of tokens because there's so many users, and so it's a lot of compute to do that. So you would like to try to do that in such a way that instead of generating one token at a time, you can generate blocks. That's difficult to do if you learn categorical distribution, because you immediately kill by the, you know, the fact that a categorical distribution of vocabulary of size V, if you generate one token, is V, but if you have a length L, it's V to the L, so you're dead. But if you do diffusion, you can actually do it by generating things like we were doing with image globally, okay? So there is a way to do that by essentially putting everything on the simplex and, you know, getting your denoiser, if you wish, to generate these one-hot vectors. And, you know, we have high hopes, like Nick and Michael are starting a company to do that, that this will generate text where instead of having to generate text where you do it one at a time, you can actually generate all sentences in one go. Much as if you combine that with the flow map, but you get something that is really efficient, okay? I'm running out of time. I have one more topic, maybe I just glance over it. There is another mode, you know, of operation of these things, which is that all what I have assumed here is that you have data, clean data and corrupted data, say. But there's a class of problem where you may not have the clean data, you only have corrupted data, but you may know what is the operator that led to the corruption. Okay, so for example, you know that your noisy image have been obtained by adding Gaussian noise and you know, grouping, averaging over pixels. Then there is a way to construct these interpolants and this diffusion where you use this information so that you can get a process that do the denoising, say, without ever having access to the clean images. And I think that's quite important for text correction or other application like that, or image correction. And this is based on a little loop where there's a self-consistency loop, which is that you say, if I have a model that denoise correctly, if I use the sample it has created to relearn the drift, I should get the same drift I started from, and you can, you know, loop upon that. And this works reasonably well. Okay, so these are examples. For example, you know, this is the one simple. Is that if you want to, you know, you take JPEG and you just give it what is the JPEG coding, and you give it many examples of noisy images at the given resolution of JPEG, it actually denoise your JPEG by learning through the collection of these guys and the knowledge of what is the JPEG compression to create.
What dimension is your simplex?
This is I'm back. Sorry, we have gone over the simplex. The simplex that for the example that I showed you is 50,000 dimensions. Okay, time 128. Okay, that's a good time. So I'm going to skip the Monte Carlo. I prepared obviously way too much, but I want to, you know, maybe insist on something because I think this is important for a math audience. If you allow me 2 minutes, I'll finish with this. Okay, which is that there is a mystery here as to why any of this is actually working. And so, you know, since I'm from Corona, I allowed myself to kind of do violence to this paper by Eijnden, which is called, you're probably, the best part of the paper is really the title. The unreasonable effectiveness of mathematics in the natural science. Okay, this is unreasonable effectiveness of machine learning, which is that there is something which is very intriguing here, which is why is any of this working? Because you all know about curse of dimensionality, you know, Bellman, thing scales exponentially. I just showed you example of images or text, right? Where the vocabulary size is like 50,000. It doesn't matter if it could be 1,000 or 100, it doesn't change anything. And you want to create sentences that are of length 128, or you're creating images where you have 512 by 512 pixels. Imagine, think about them black and white. That's a vector in R to the 512 by 512. How is it possible that we can learn anything in dimension that are as high as that? Like there's a big mystery here that is really only, you know, a little bit touched upon. Intuitively, it's clear what's happening is that we know that the curse of dimension is there and is there to stay. And so that means that the data that we have, text or image, is extremely structured. It's not as high dimensional as it seems if you were just to do a naive counting argument. but what is the structure of this data, and when will this model work or not, and what's the interplay between why they work and the architecture, why are transformers so much more efficient than previous architecture, is something that is for the most part open. Okay, and I think these are very interesting, maybe too hard mathematical questions, but certainly questions that I was while thinking about. Right? These are these questions. Why? And I would like to argue, and this is my final point, that by and large, machine learning and artificial intelligence is an experimental field. There's a new gadget, and people are exploring all the kind of things that you can do, and that's what's exploring. But I'd like to argue that there is still a need for theory, which is good news for us. With two little graphs here, that this one especially is scary, and that's going to be my ending. This is showing you on a log scale the improvement that you have in performance of these models when you increase the data set. And in general, it's pathetic. This is what this says. Okay? So that means that machine learning models are really data hungry. Okay? And that is something where, nowadays there's a lot of like fine tuning and, reinforcement learning strategy just to try to solve this problem, because the internet and the data available on the internet has been used. So we need to do something better if we want to go with this curve higher, and this is not good news if we stay there. We need theory there. This one is a bit more scary even, so I don't know if you can see the scale, but this is the training compute in flops. This is really the beginning with AlexNet and these things over there. This is 2000. And then this is when really deep learning started over, in fact, the generative AI. Okay? And this graph is actually telling you that the compute that is needed to build this model, but these days, on top of that, we need to put inference, is actually increasing by a factor over 4 per year. That's way worse than Moore's law. Moore's law is dead, but when it was working, it was not working at that rate. Okay? So, this is the scary part. We are 10 to 26 years. That's a lot of kilowatts, I can tell you. And so that also tells you that we need to do better. This is on the example that we have done, right? This is what happened if you just increase the transformer size. This is this axis, if you wish. Take the same data set and just increase the size of the network that you train. And what you see is that, and this is this phenomenon of this plateau that is in training, that something reasonable only emerges past a certain size. Right? So these are you need, and that's that. But if we want to do better these days, we really need to increase. And I think that this is something that is worthwhile thinking about, which is, are there better ways to do that so that we can get better training, better architectures, etc. And that's it for today. Thank you.
Is there any question?
Here in the lab, one of the core of the lab is adaptive sampling. So what I've seen is that in generative model, they take t from 0 to 1, and they take it evenly spaced with the Euler or second order tuning method. And so you said that you can replace the 1 minus t and t by square root of whatever. Is it equivalent to adaptive sampling? And maybe on this time scale between 0 and 1, typically looking at relative when doing ODE, you say, okay, here I need to take a smaller step because I know that there's a key point in my ODE between 0 and 1. Have you tried doing, or is it equivalent to the SD trick? Is it something similar, or just changing the T?
So with several aspects. So what we have tried to do is that in this multitask, right, you can decide that instead of working an operator, you do something which is simpler, which is that you give yourself one alpha, and then you say the beta, the other coefficient, so f of alpha, with the right monetistic. This is in some sense, there's no scale aspect, but it's just kind of telling you at which schedule you should put noise and data into it, and you can optimize upon that. But indeed, all of the second part is about this, which is that if you learn these multitask interpolants, or if you learn the diffusion coefficient, or if you learn the flow maps, you allow yourself to do generation. Well, for example, in the flow maps, I show you that you can do generation in one step. but you could do generation in 4 steps. That's not much more expensive. And then you could optimize what are the steps that you need to do. Okay. And of course, the way we have thought about it so far is like it's a 2-level way. You just need to train first this thing, and then you use it at inference in different modalities to make it more efficient. But the right way to do it would be with a feedback loop, where you use that to go back into training, and so that you feed on itself so that you get things. This is also completely open. The problem is that it's really something which is, again, fairly experimental, in the sense that at the end, the choices that you need to make there depend on the structure of the data distribution on which you use them. And so you can make a lot of analysis, for example, if you go from Gaussian to Gaussian mixture. But that is not very interesting from a practical standpoint. And if you go to text or images, okay, there are many works, Simoncelli, Florentin Gouth, Giulio Berri, Stefan Mala. There's many people that are working on this, but I would say it's only the beginning. We don't really understand what's going on.
And on that, we think that we might find general methods for example, choosing the right discretization in time that would work both for, let's say, proteins or images or video. Is there a general structure to be captured, or we really be specific to a certain type of signal, be text, be image, be whatever?
That's another very, very interesting and very hard question, because the tasks on which machine learning has been efficient so far, okay, are clearly tasks where the data has some structure. And a posteriori, it's sort of clear that the data should have structure, because there is sort of a machine learning or a Gen AI that is actually capable of processing them, and that's us, right? If there was no structure in text or images, you'd not be able to process them either, right? But an interesting question, if we go into other application, is to see whether other application domain also have sufficient structure. It's not guaranteed a priori that proteins beat the curse of dimensionality. These works seem to say that it does, but let me give you an example. If you want to sample, I don't know, a glassy system, then clearly this will probably not work. Right? You can construct adversarial example in which the learning is impossible. Right? And a big question is to know, if I give you a domain application, you want to do that for medicine, you want to do that, to kind of analyze genome or things like this, in which class is that exactly? These are, I think, fascinating questions.
On one slide, you had written quantum field theory, but you went through the slide too fast. Did I hallucinate?
Well, there was just, but it was just 5-4. So it was like a baby bird. So, I mean, the idea there is, you mean this one?
It had a picture or something, and then, I don't know. Yes.
This guy?
Yes.
Okay, so I didn't discuss that. That's another very interesting area, which is, many people in Gen AI say they do sampling. But in fact, they don't really do sampling, because there's a big cheat. You have the sample to begin with. Sampling, in principle, should do Monte Carlo. But Monte Carlo is a completely different modality, because it's a modality in which you have, a model, but no samples. And so, there's a chicken egg problem there, which is that to build these generative models, right? Okay, so what I wanted to discuss here was this. You can think, I told you, if you have a generative model like that, sampling becomes easy, right? That's true, but it's only true if you have been able to learn it, and to learn it, you needed the data. When you want to do the Monte Carlo sampling, the aim, of the game is actually to generate the data, and so you have a, chicken egg problem. But there is something which is interesting in this, which is that this is verifiable AI, in the sense that if you have an oracle, as they call it, a model that you want to sample, right? Unlike for images, you can validate your model. Validating images is, there are tricks, but essentially we don't know the distribution. If you know the distribution, like you want to do, QCD or 5-4, well, in principle, you can check whether these are samples that have the right likelihood, because you know their likelihood from your model, right? So that's another very big area where this model could be useful, and it's only beginning for the reason I just explained, which is that if you have no data, it's hard to start.
Yes, thank you very
Oui,
much.
en fait, on peut voir.